let's see. So I'll put this on. Yes.
Perfect.
Yeah. So again, thank you very much, Rupa Manjari. I hope I said your name correctly.
Yeah, Barry calls me Rupa. That's easier.
Oh, Rupa. Okay.
Yes.
Thank you very much for the very elaborated introduction. I really appreciate it. Thank you. And thank you for the rest, all the other organizers, for giving me this opportunity to speak here and to tell you a little bit about my recent work. I'll be talking today on the role of quantum coherence in thermodynamics. This is a very, very recent work of mine that I just recently posted on the archive. It's appearing here. And let me just double check. Can you see my cursor when I move it, just so that I know?
Yes, we can.
Okay,
yes.
Excellent.
Thanks.
So I'll be talking about this work, and my talk will have two parts. I will talk about quantum coherence, and it's not really just, perhaps a more precise name for it is more asymmetry, and I'll explain it in a minute what I mean by that. Or time translation asymmetry. So that's the type of coherence that we see in thermodynamics. And the other part of my talk will focus on thermodynamics. So I'll first want to a little bit talk about some quantum coherence, tell you a little bit what we know about it, and then talk about thermodynamics and see how coherence play a role in thermodynamics. So let me go right to the question of time translation symmetry. So what is time translation symmetry? So we say that a quantum state, and I will denote here this kind of like D represents the density matrices that acting on system A. And when we have a density matrix acting on it, we say that it's a time translation invariant with respect to some Hamiltonian on the system A. And it's time translation invariant if it satisfies this kind of equation, if it doesn't change under the evolution over time, right? So the system evolve over time, it doesn't change if the state is invariant. Now we can also extend this definition a little bit more to quantum channels. And then we say that the quantum channel is time translation invariant, it's time translation, sorry, covariant. For quantum channels, we use the term covariant rather than invariant. If it also, in a sense, commute with the channel, the evolution commute with the channel. We can see it in this following diagram. So you can see if I look at the state rho and I apply a quantum channel to it, I end up with this state. And then if I apply a time evolution, I'll end up with this state. Maybe I forgot to mention that I consider here a possible that the Hamiltonian of the output system, B, may be different than the Hamiltonian of the input system, A. And we say that the channel is time translation covariant if for any state rho that we input into the system, whether we first apply the channel and then let the state evolve, or first let the state evolve over time and then apply the channel, we will end up with the same state here at this location. So if this happens, then we say that the state is time translation covariant. Now, this is the set of all time translation covariant channels form what we call a resource theory. We can ask questions typically what type of transformation we can do with such channels. And this is what I will try to discuss. But before doing that, I want to discuss a particular interesting channel, quantum channel of this type, very fundamental channel. It's called the pinching channel, sometimes called also the twirling channel. When you have a Hamiltonian, and you write the Hamiltonian as the sum of projections. So it's the spectral decomposition, except that here we have perhaps projection because we might have degeneracy. So if we have a degeneracy, this capital pi here just represents projection to an orthogonal subspace of system A. And this pinching channel just destroys all the coherence because it just projects to the energy eigenspace of the system. And this channel has lots of nice properties. First of all, it is time translation covariant. It's relatively easy to show. It also has this property that it's idempotent. That means if you apply it twice, nothing happens. It also can be used to tell us when a state is time translation invariant. If it's time translation invariant, if and only if when you apply this channel to it, nothing changes. And another interesting thing that would be useful for me here in the talk is that a channel is time translation. If a channel is time translation covariant, then it commutes with this channel. And finally, the Pynchon channel can also be expressed as a random unitary channel. So it has many nice properties. But one of the nice, for me here is even a more useful property is that it can be used to quantify asymmetry. I can ask how much a quantum state, we know so that a state is invariant if P of rho, if the pinching channel when applied to rho is equal to rho. But I can ask a question, how much, when a state is not invariant, how much not invariant it is, how much it has a time translation asymmetry in it. And one way to quantify it is a well-known method to quantify such state. It's known, the relative entropy is used for that. It's a kind of like a type of a distance. And we're asking the question to quantify how resourceful or how much a state doesn't have asymmetry, that is not time translation symmetric, or in other words, it has time translation asymmetry, is by how far it is from all the invariant, the set of all the invariant states. And the way we measure how far it is from the invariant states is by this relative entropy measure, that it's kind of like a pseudo distance, but it turns out to be the right quantity to work with. And when we looking at this distance, the inf here means just time translation invariant states, all the states that are invariant under time evolution. And if we look at the minimum of this, it's relatively easy to see that it's actually equal to the difference between the entropy of the von Neumann entropy of the twirled state, or the state after we apply the pinching channel, minus the entropy of the state rho. And another interesting properties of this measure of coherence that I want to emphasize and will be useful to us later is that actually time translation asymmetry grows logarithmically when we're taking many copies. So the coherence, that's what I call this measure, the coherence of rho, grows logarithmically if you take n copies of rho. It's possible to show. And in particular, many times in quantum information, we take a quantity and we regularize it. And it turns out that this regularization has operational meaning. But in this case here, what we can see is that when we regularize this quantity, we're actually getting zero. That's why coherence is a very subtle property, and one has to kind of treat it somewhat differently than what we are kind of usually using in quantum information. And so having this in mind, I want to share with you some result about this quantum coherence that I recently found out. And the first result is relatively simple. It just says, suppose that you have two Hamiltonians, HA and HB, and I am considering Hamiltonians that are oh, so I see here, by the way, that someone asked a question whether we can take C of rho with a max rather than a mean. No, because let me go back here. We cannot take the maximum because we are interested to know we want a measure that would turn out to be a measure of a resource. That means you cannot increase the coherence. I'm happy you actually asked the question, because why I'm using this measure? Because this measure has a very important property that I completely forgot to say, that is very important, that when you apply covariant channel to this state, the coherence cannot increase, right? You cannot increase coherence, you cannot increase asymmetry with operations that are covariant, with time translation covariant channels, because time translation covariant channel cannot create more asymmetry. It can only make things more symmetric. It cannot make things more asymmetric. So it cannot create coherence among energy levels. It can only destroy coherence. So this measure has this property that when you apply the channel that is time translation covariant, it can only decrease. On the other hand, if I put here a max, that won't happen. So that's why we have to take the minimum. Okay, so let's go back to this question. So now let's take two Hamiltonians, and suppose that those two Hamiltonians have this property that something that I like to call relative degeneracy. Now, what does it mean? Degeneracy, we say that this Hamiltonian is degenerate if for some of the two eigenvalues are equal to each other, right? Relatively non-degenerate Hamiltonians would be Hamiltonians for two Hamiltonians. If I consider two Hamiltonians, I would say that they are relatively non-degenerate if I look at the differences between them, and I see that the differences of this Hamiltonian, if it equal to some difference of these two Hamiltonian, the only way it can be is if x here equal x prime, x is an integer, and x prime, y, and y prime in this talk are always integers. And if those things are equal, if this is equal, then it means x equal x prime, or alternatively, and y equal y prime. So the only way is that if this is 0 and this is 0. Now notice that even though this is a strong condition, in fact, almost all Hamiltonian satisfies this. In fact, it's a full measure. Like if I pick up two Hamiltonians at random, they will actually satisfy this. Now, one of the remarkable property is that if two Hamiltonians have this kind of generic, in this sense, that they are relatively non-degenerate, then a channel is covariant with respect to these Hamiltonians, if and only if it is a classical channel. What does it mean, a classical channel? It means that when you apply, you see the pinching channel for these Hamiltonians is essentially the completely dephasing channel, because those Hamiltonians are non-degenerate. One can easily see that if two Hamiltonians are relatively non-degenerate, then each one of them alone is also non-degenerate, right? Because if this equal to 0, then it means that the only way this is 0 is if x equal x prime. So that means that this is also non-degenerate, right, in the usual sense. So relatively non-degenerate Hamiltonians is a stronger notion than non-degenerate, separately non-degenerate, each one of them. So if they are non-degenerate, clearly the pinching channel is the completely dephasing channel. And in this case, it just means that everything is classical with respect to the basis associated with those pinching channel, with respect to the Hamiltonian basis, to this basis, the eigen basis of these Hamiltonians. So this is essentially really a classical channel. That's the only way that the channel is covariant. It commutes with the, it's a time translation covariant. Okay, so this is a nice thing, but this immediately tells us that if we want to get something interesting, we cannot consider Hamiltonians that are relatively non-degenerate, even though this is quite generic. Another important example of Hamiltonian is when we have the input is equal to the output. In this case, this Hamiltonian is two Hamiltonians that are equal, they cannot be relatively non-degenerate. And so for Hamiltonians that if I consider the input and the output to be the same system, then I can consider the non-degenerate Bohr spectrum. This is another notion of non-degeneracy that says the following, that the spectrum has a non-degenerate Bohr spectrum if its differences are equal only if and only if either x equal x prime and y equal y prime, or alternatively x equal y and x prime equal y prime. So here we have two options. And this is also a very popular scenario because in fact, almost all Hamiltonian satisfies this. It's very generic. And in this case, we have a very interesting result that I want to discuss here. And what I want to talk about is a problem that we ask a lot in resource theories. We're asking, can I convert one resource to another resource? In our case here, can I convert one state that is asymmetric to another state that is asymmetric? Under what condition I can convert, I can imply a conversion like that if the conversion is done by a covariant channel. So let me be more specific what I'm trying to say. So suppose that you have a system, two density matrices of the same system A, and they have a Hamiltonian HA. And suppose that the Hamiltonian has a Bohr energy spectrum. In this case, if the two channels are related by a covariant channel, covariant with respect to this Hamiltonian, then it turns out that you can actually specify exactly what are the conditions that such a channel exists. And such a channel exists if and only if this a certain matrix that we can call it Q is positive semi-definite. All its eigenvalues are non-negative. And what is this matrix Q? It's just a matrix. I don't have to go in too much details, but it's just some matrix that defined with respect to these components of rho and sigma. So it's very interesting. You can take rho and sigma, compute its components, construct a matrix, check if that matrix is positive semi-definite. If it is, then there exists a channel and that is covariant that it can take rho to sigma. So this is an if and only if condition. Those two conditions here are equivalent. So this is kind of like a nice, interesting result. The reason it's interesting is that it's kind of surprising that one can actually get a precise condition, a closed formula to determine whether a covariant channel exists between two states. But now I want to show you why this is useful and how I can apply it to thermodynamics. But before I go to thermodynamics, I'll just say one quick corollary of this theorem is the following, that you can always convert a pure state to a mixed state. That is, suppose that you have a density matrix sigma and denote its diagonal elements in the energy eigenbasis of the system by px. Then you can construct a pure state, and our theorem before, this theorem, can be used to show that in this particular case, you can always find a quantum channel that is time translation covariant that take psi and map it to sigma. Okay, so it can always convert a pure state to a mixed state. Okay, so now I want to go and to tell you why this theorem is useful and how we can apply it also in thermodynamics. So let's go back to thermodynamics and remember what is really thermodynamics. So in recent years, there's been a resource theoretic approach to thermodynamics has been developed. And in this approach, we consider systems that are outside of thermal equilibrium as resources. The reason they are resources is because you can extract work from such systems. Systems that are not in thermal equilibrium are usually denoted by gamma. They are called described by Gibbs states, and a Gibbs state of a system A would be denoted like that. A Gibbs state of a system B with Hamiltonian HP will be denoted as gamma B. This will be our notations for the Gibbs states. Now, the Gibbs state has many interesting properties that I just mentioned, 3 of them here. That are relevant to us. One is the Gibbs states cannot be used to extract thermodynamical work. Gibbs states also has minimal energy for a given entropy. So they are really the state with the least amount of expectation energy. And also Gibbs states are also known to be the only states that are completely passive. In some sense, it's kind of an operational, it has an operational meaning that the Gibbs states, even asymptotically, cannot be used to extract work. I don't have time to go into details what this last thing means, although it's a very useful property of Gibbs states. So this motivated the idea of treating quantum thermodynamics as a resource theory where the Gibbs state formed the set of free states of the theory. But note that the Gibbs state is, of course, depends on the Hamiltonian, and for every different Hamiltonian, the Gibbs state looks differently. So Gibbs state, and in fact, there is a one-to-one correspondence between Gibbs states and Hamiltonians up to an energy shift. So this one-to-one correspondence hold as long as, because the Gibbs state is invariant under energy shift, and the total energy shift doesn't affect anything. That's why Gibbs state is a convenient way to describe the physical system in terms of a resource. So resourcefulness in quantum thermodynamics can be viewed as how much states are different than a Gibbs state, how different they are. The more different a physical system is from a Gibbs state, the more resourceful it is, the more you can use it to extract thermodynamical work. Or you can try to use a system to cool another system, and so on. There are lots of tasks that can be used by states that are actually not in thermal equilibrium. But to develop a resource theory, we have to talk about what are the free operations in this model. So we identify the Gibbs state as being free. And in general, what we can imagine is that we can take a heat bath at a particular fixed temperature that is given in a Gibbs state, that the heat bath is described by a heat state, a Gibbs state. And we can imagine some quantum system A interacting with this heat bath, going through some interaction, perhaps exchanging heat, exchanging particles. The system here is not a single atom, even though my picture here is written like a single atom, but it could be a relatively big system or a very small system, doesn't matter, but it's some quantum system. It can interact with the heat bath, and at the end, get outside of this interaction and end up with another system. And we can ask the question, what kind of operation, what type of operation, what this can be represent, what is the most general things that we can do to a quantum system in a thermodynamical sense when we can only consider a Gibbs state as being free. To do that, we need to classify the type of operations we can apply. So we already saw, and I kind of told you that I consider the Gibbs state as free. So I will define thermal operations or free operations as operations that allow me to prepare Gibbs states. That's at least one thing they can do. So any subsystem B with some bath, typically I can think about it as a bath, so that's why I'm using the letter B. With some Hamiltonian HB, I can prepare a Gibbs state, a system in the Gibbs state gamma B. This I would assume to be free. Another thing that I will assume that is free is that the system and the heat bath are evolving under evolution that conserve energy. So I'm allowing from an evolution that conserve energy between the system and the bath. And the last step is that, of course, we can discard some subsystems. We can trace out subsystems of a composite system. So these are kind of three very basic steps to say what we can do to a thermal or to an athermality state that is actually not necessarily in thermal equilibrium. But what we can do to it, we can append it with a Gibbs state, we can apply a joint unitary, and we can trace a subsystem. Those three steps can be characterized as follows. You have a system here, and I take the bath state, it's in gamma B. I take my system rho A, I let it evolve unitarily under an energy preserving evolution. And then I can trace out the heat bath system and end up with the state that is given here, which is essentially appending the heat bath, then applying a preserving energy unitary, and then tracing out the subsystem. These are called thermal operations. And we can think about the commuting of this with the joint Hamiltonian. It can be shown that if it commutes with the joint Hamiltonian, it's equivalent if this unitary channel, which is just this channel, preserves the Gibbs state. So preserving the Gibbs state is equivalent to commuting with the Hamiltonian. And Gibbs states of two systems with well-defined Hamiltonians can be also decomposed as a tensor product. Always this is the case. Okay, so these are thermal operations. Now, maybe you may raise the question, why do thermal operations always constitute that A can go to the same A, or can I go to a different system here? Can thermal operations allow me to go somewhere else? And the answer is yes. You just need to consider Gibbs preserving unitary channel, AB, that in this time, rather than the system AB and A prime are completely different than AB, they have different Hamiltonians. So those are completely different states than these ones. But I only assume that the dimension is the same so that I can define a unitary channel. And then one can show that the original definition that we defined before to be thermal operations can be extended and can be, in fact, this is a lemma rather than a definition. It can be shown that if this is possible, then also this is possible. It's possible to show it. It's not super trivial, but it's possible. So in fact, any operation like that is also a thermal operations, as long as this unitary channel preserves the joint Gibbs state. Okay, so having understanding what thermal operation is, let me tell you one thing about thermal operations is that, again, the pinching channel that we spoke last time is also a thermal operation. And I denote here thermal operations as channels. TO A for A prime will be how I define thermal operation from system A to system A prime. I'll denote it like that. These are thermal operations. It's a set of all completely positive trace preserving or quantum channels from A to A prime. But yes, yeah. So thermal operations has two problems with them, actually, the thermal operation that I spoke with them. Two undesirable properties. One of them is that it is actually, they are actually not closed. It's not a closed set of operation. And this is very unphysical. What does it mean not closed? It means that you can find a sequence of channels here. All of them belong to A to A prime, that they have a limit. This sequence of channels have a limit in the set of all quantum channels, and that limit is not thermal operations, even if the set of quantum channels is a thermal operation. So this is kind of an unphysical property. Where is this property coming from? Why we have this? It's because if you notice in the definition of thermal operation, this can be any Gibbs state and the system B can be any Hamiltonian. So in fact, the dimension of the system B here is unbounded, and you can take any dimension. If when dimensions are unbounded, it always happens in physics when you allow for dimension to be unbounded, then there is all kinds of discontinuity occurring or certain things. We have to be kind of careful with this. And so this is where it's coming from, that the dimension of system B here is unbounded. That's why thermal operations are not closed. And in fact, they are also not convex. And we can actually resolve both of these problems by taking the closure of thermal operations. And so taking the closure of thermal operation, what does it mean? It means that I say that I'm considering the set of closed thermal operation to be the set of all quantum channels that can be written as a limit. And the limit here is understood in terms of Choi matrices, right? You can take the trace norm of the Choi matrices between those channels and those channels, it goes to zero, the difference. Essentially, the channel just approaching to this channel. And if all the channels are thermal operations here, we expect that the limit would also be a thermal operation. So defining this set, it includes, of course, the set of thermal operation, but it is a larger set than thermal operation. And in fact, this set, by definition, this set is closed, but more interestingly, this set is also convex. And this is very useful property when you work on and do certain calculations. When you're working with a convex set, is very convenient mathematical property, but also has some physical significance as well. And so I will be working with this set rather than with thermal operations, as this is in some sense more physical, because we have to consider the set has to be closed. And not closed systems would lead to all kinds of strange behavior. Okay, now there is another type of operations that thermal operation and closed thermal operations form a subset of it. So it turns out that thermal operations and closed thermal operations has two very, very interesting properties. The first one is that they are Gibbs preserving. This means that if n is a thermal operation, then when you apply the Gibbs state to it, the output will still be Gibbs state. Notice that this is not a unitary channel. This is a thermal operation, the operation we discussed before. So what it means is, if I go back here, it means that if I put here the Gibbs state, then the output would still be a Gibbs state. It's because I get here two Gibbs state, and this is Gibbs preserving, so I'll get the Gibbs state. So it's Gibbs preserving. But the second nice property is also time translation covariant operation. And so this leads us to a plethora of different types of operations in the resource theory of thermality or of quantum thermodynamics. We discussed already the thermal operations and the set of closed thermal operations, but I can also define Gibbs preserving covariant operations. Gibbs preserving covariant operations are precisely those operations that satisfies these two properties. It can be shown that those that satisfies these two properties form a larger set than the closed thermal operations. And they, however, it is a very big open problem in the field, is whether these set of operations have a stronger power than this set of operation. It is known they are bigger, but sometimes being bigger does not mean that you can do something more than this set of operation, meaning that if I can convert rho to sigma with this set of operation, the question is whether it implies that I can convert rho to sigma with this set of operation. This part is not known. We don't know if they have the same conversion power. And then there is another set of operation known as Gibbs preserving operation. This is a much larger set that just requires the first property here and ignore completely this second property. And people studied thermodynamics in terms of all of these set of operations. Let's see, I have a question. Yeah, so I will say close. Yeah, so when I call closed thermal operation, I don't mean in terms of open system versus a closed system. I just mean taking the closure of this set of operation. So it's not about being a closed system or open system. Thermal operation, in fact, defined with respect to closed system because we have system plus heat bath, and we looking at the combination together of those two systems. So we're looking at them as a closed system, right? Because we're considering energy preserving unitaries. And then we're tracing the subsystem. So we're also looking at open system in this case, but after we're tracing out some subsystems. But the notion of closed here, I'm happy you actually asked, it's not about the system being closed, it's just about being taking the closure of this set, because this set is not closed. So you have kind of strange things. If you take a sequence of operations, suddenly they allow you to do some, the limit is not allowed, but each element is allowed. So it's highly non-physical. Anyway, so these are the set of operations that we have in thermodynamics. Now, how do we quantify our thermality? You know, there is a very nice way to define our thermality, again, using the same idea of the relative entropy distance to the set of free states. But here, the set of free state is the gamma, the Gibbs state. Now, I will not go in details here, but I will just say that this relative entropy distance can be written like that, right? This is the von Neumann entropy. It's trace rho log rho. And what is written here is the relative entropy between rho and gamma. It can be shown that this quantity can be written as the difference between the two free energy, the free energy of rho minus the free energy of gamma. But I don't want to write it like that. I want to show you another interesting way to write this relative entropy of distance. This is a measure of athermality. So if you give me rho, a system rho, with a given Hamiltonian, so then the system has a given Hamiltonian, therefore it has a given Gibbs state. Then I can compute this quantity, and I claim that this quantity quantifies the athermality, how resourceful the system is. It turns out, if you look at this quantity, because gamma is time translation invariant with respect to the energy eigenbasis. So I can write it, I can apply the pinching channel to rho here, because this system is diagonal in the energy eigenbasis. So it's like I'm doing nothing. But what's interesting is that then I can write this whole thing slightly like that. And if you notice, what I'm trying to get into is the following observation. We're trying to quantify the athermality, the quantum athermality of a given system. And this quantification has two parts to it. One is the pinching channel. We remove all the coherence from rho, and we end up with something that I will call non-uniformity. I'll explain it later why I call this non-uniformity. And the second quantity here, this guy, if you remember, this was the quantum coherence of rho. So we can see that the quantum athermality comprises of two types of resources. It comprises of something that I call non-uniformity. I'll explain it in a second. And from the quantum coherence. And we will see this in everything that I talk about. There will always be this kind of the resource of quantum thermodynamics is, it always comprises of two types of resources. One is the coherence, and the other is more information. It's more like informational non-equilibrium of a system. So it has an informational non-equilibrium. The more non-equilibrium the system is, the more in a state of non-equilibrium the system is, the more resourceful it is. And the more coherence it has, the more resourceful it has. So it's very nicely written here in this measure of quantum athermality. We see that this measure really split nicely into these two different ways. To even emphasize it further about this splitting is suppose that a quantum system, suppose you have two quantum systems that have the same diagonal, the same non-coherence. So they are only different in their coherence. They have, if I apply the pinching channel, then I destroy all the coherence of the state rho, and I apply it to sigma, I destroy all the coherence that I apply to sigma. So what I'm left with is more of the diagonal terms. So but that state can be, if the state have the same diagonal, and so they are only, the rho and sigma are only different in their coherence, then it turns out that there exists a Gibbs preserving covariant channel that can take rho gamma. I emphasize it, the system here, I write them as a pair because I have the physical system described by rho, but the system also has a Hamiltonian, and its Hamiltonian is described by the Gibbs state. It corresponds to a Gibbs state. So if I look at the conversion of one system to another under Gibbs preserving covariant channels, if the rho and sigma has the same diagonal, then the Gibbs state doesn't play any role. It doesn't matter what the Gibbs state, what's the Hamiltonian, and the conversion is possible if and only if you can convert rho to sigma by time translation covariant operations. So the only factor that determine a conversion is just the coherence. So what we can see that only if the states has the same after you apply the pinching channel, if you have the same state, you end up with the same state. So any manipulation of the coherence from one state to another is only determined by coherence consideration. It's only determined by the same matrix Q that I discussed earlier, and it's only if it's positive, and it only depends on rho and sigma. It does not depend on the Hamiltonian. It does not depend on the Gibbs state. And this is why, if the systems have the same, I will say, non-uniformity, that's what I called it, if they have the same diagonal, then only coherence determines the conversion. Now, let me tell you what I mean by non-uniformity. Suppose that you have a system that commutes, rho and gamma commute. So then if they commute, they have a common eigenbasis, and I can really view them as a probability vectors. Like I can view it, this is like a diagonal matrix, right? Because they commute, so I can write them both as diagonal in the same energy eigenbasis. And so then I can identify any density matrix with a probability vector. So this is a probability vector. And this is the Gibbs state has a probability vector GA. Now, it turns out that in this quasi-classical case, there is a very nice result that go back already to 2000. Sometimes this result was rediscovered later on, but it turns out that if I go back in time to 2000, remarkably, this has been actually shown exactly what I write here, is that you can convert a pair of states, right? Remember that now probability vectors are just diagonal density matrices. So in this regime that everything is diagonal, converting one system to another by closed thermal operation is equivalent to the conversion under Gibbs preserving operations. So Gibbs preserving have the same power as closed thermal operations. Now, Gibbs preserving operations can be written as you can go from here to here by Gibbs preserving if and only if there exists a column stochastic matrix that takes the vector P to another probability vector Q that is given here, and takes the same column stochastic matrix, also takes the Gibbs state of system A to the Gibbs state of system B. And this is precisely known as something called relative majorization, where this is essentially the definition of relative majorization. It's related to a concept of majorization studied in entanglement theory too, and I won't go into it much. We don't need it too much. I will only say that the reason I like to call non-uniformity is that there is a remarkable property in the quasi-classical regime. Oh, I have a question here, so let me see. Yeah, so I'll answer maybe at the end about questions about I see some other question. I'll answer them later because I am actually running out of time. So let me finish first and then I'll answer some more questions. Okay, so we're getting into the quasi-classical regime, and the interesting property that happens here is that if I look at a system with a trivial Hamiltonian, its Gibbs state is a uniform state. Trivial Hamiltonian is a zero Hamiltonian, or Hamiltonian that is completely degenerate. And it turns out, and I'll denote the Gibbs state when it's uniform, I'll denote it by the letter U. And a remarkable property is that if the Gibbs state has rational components, then it is always possible to show that under closed thermal operation, you can convert any state to a system with trivial Hamiltonian. So essentially, in the quasi-classical regime, the athermality of a system is completely characterized by non-uniformity, by how much the system R is different than the uniform state U. And it's possible to show that under CTO, those two resources are equivalent. Because they are equivalent, I can go from here to here and here to here by CTO. It means that they are the equivalent resource, and therefore one can convert one system to the other by closed thermal operation. It means that the resourcefulness is in fact, the resource here is in fact non-uniformity. It measured by how different R is from the uniform state. This is why in the quasi-classical regime, the resource of quantum athermality is non-uniformity. And this is why we will consider the golden unit in quantum athermality as a non-uniformity, where we're taking this to be a pure state, and this is the maximally mixed state. And this is a measure, this is like an E-bit in entanglement theory. Those of you who know entanglement theory know we're using E-bits to quantify entanglement. Here we can use the bits of quantum athermalities are two-dimensional A with U, written like that. Now, it turns out another way to characterize it is that if the dimension is not 1, it's possible to, is not 2. In fact, it's possible to bring it to a two-dimensional system, classical system, where X is a classical system, its dimension is 2, and U here is just diagonal matrix looking like that. So it turns out that I can, in fact, characterize any number of copies of this resource and also any number of dimension for any dimension A. I can always bring it to a two-dimensional system. So in fact, this is a very interesting golden unit, we call it, to quantify quantum athermality. And to define quantum athermality, because I'm out of time, you know, what I'll just do is I'll just say that we're using this golden unit to quantify the distillable rate. And I'll just say very nicely that there is, in a single shot regime, one can define how much you can distill a quantum system. And you can do that by defining how close you can come to a given state sigma, and how close you can come to this golden unit, and how big, how resourceful this golden unit can be. And the more resourceful it is, the m represents how resourceful it is. If m goes to infinity, if you look at this golden unit, when m goes to infinity, those two vectors are orthogonal. This represents an infinite energy. And this is the most resourceful state, is when m goes to infinity. We have that the Gibbs state has a 0 eigenvalue, because this is the Gibbs state here of this system. So I will just mention that when you measure the distillation, you will get a very nice result, that it is the distillation actually determined by the hypothesis testing divergence comes into play here. And it's really giving an operational meaning to the hypothesis testing divergence in terms of a distillation, how much distillation of M I can have, how much I can distill the resourcefulness, how much I can distill a quasi-classical athermality from a given state rho. And this can be done asymptotically, and it implies, it gives another operational meaning for the quantity that I defined before, that rho, the relative entropy of rho and gamma, really quantifies how many copies of a golden unit I can distill from many copies of rho. Now, the problem that we're facing in thermodynamics is that in the opposite direction, when I'm interested in the cost, I can ask how many golden units I need to use to distill, to form, to create a given athermality state rho. And in this case, the problem that we're facing is that the state here is quasi-classical and the state here is not quasi-classical, so we cannot generate coherence. This doesn't have coherence, this system here, whereas this system has coherence. And so under Gibbs preserving operation, we have some nice result. It's given by Dmax, by the smooth Dmax relative entropy. But under the more physical set of operation, which is closed thermal operations or Gibbs preserving operation, the cost is infinite because for small enough epsilon, because we cannot convert this state to this state. And so because of that reason, there was a paper, one of the seminal papers on the resource theory of athermality, invoked an idea that said, hey, you know what, let's allow for a sublinear amount of energy, because sublinear amount of energy is like we're allowing very little energy to the system, because asymptotically, when I take n to be very big here, per copy, this is like a relatively small amount of energy. So what they were claiming is that, so maybe before what the paper was claiming is, when I consider a conversion, I can convert the quasi-classical state to many copies of this system of rho. It means that I allow for a sublinear system. So that's what it means. I'm saying I'm taking this resource, I add to it a little bit of coherence, but this coherence is asymptotically little, in the sense that n here goes, the alpha here is smaller than 1. And in this way, I can achieve this transformation. And the main idea, the main result is that I wanted to present, that even the cost is given by the same quantity, and therefore the resource theory is reversible. However, I was only able to prove it for pure state, and the original statement in this paper is actually incorrect. So it's really it's incorrect, that there is no proof, that the proof is incorrect. So right now it's an open problem in the field to find if it's really true that if I allow for a small amount of coherence, asymptotically, that it's asymptotically vanishing, the rate of the coherence that I'm using, whether I'm able to establish reversibility, whether the distillation equal the cost of preparing a given state. Okay, so I think I'll skip my open question here and I'll just say thank you because I'm out of time. And I know there were also some questions. So yeah, thank you very much.
Thank you very, very much. It is a very clear and organized talk, and one could see the rigor of the work. I learned a few things. This is all about what I understood, reformulating thermodynamics as a resource theory, and you talked about this resource called athermality, and that consists of two parts, right? I mean, the first one, I have to still read a bit what you called information non-equilibrium. And the second one is very clearly explained, time translation asymmetry, or what you quantum coherence.
Right.
So I think it's really, really interesting to learn from you directly about the resource theory of quantum athermality. It's not all done. There are open problems. And I saw that you are also advertising for more hiring in your group. So the students who are listening to you, is an interesting area. And I think there are open positions in this. With this, I will open it up for some quick questions, Prashant, time permitting. So,
sure.
So I think students, you can just raise your hand and then unmute yourself and talk, or you can use the chat box as well. Please go ahead. Thanks a lot for this.
Yeah, thank you. Yeah, I can see that actually there is one question that was referred, I think, directly to me. That it says, "What the difference between?" So the question is, I didn't speak about thermodynamic cycles, Launder principle, information is physical, and all that. Yeah, I mean, I had so much to talk about, and so I chose one particular line of reasoning that is based on the main result that I was trying to present. It is true that there is a law. Thermodynamics is a very big, very, very big subject with lots of interesting questions and lots of history, actually. And honestly, I mean, there's not even consensus on how to formulate even the second law of thermodynamics, even today. So it's really, it's really not one single talk cannot cover those things. It is, though, very interesting that what happened in recent years is that we worked on quantum information, then we realized that quantum information can be formulated, even quantum information, as a theory of interconversion among resources. All the computations of capacities and stuff like that, those are interconversion among resources. They can be dynamic, like a quantum channel, or static, like entanglement. They can be noisy, noiseless, static, like quantum, classical, private even, or public. That's more in the context of cryptography. So everything can be formulated as a resource theory. And in recent years, we also expand more and see that also thermodynamics and many other areas in physics can be formulated as a resource theory. And so in this model, we're using all those tools that we know from quantum information, and we apply them directly to thermodynamics. And I think this is what makes it really fascinating to see how you actually can use a lot of the tools that we worked in just pure quantum information theory and apply them to such a physics theory, prevailing theory as thermodynamics.
Indeed. And this slide that we can still see is a very critical one.
Yeah, I think this is a very nice slide that actually characterizes it all, showed and demonstrate. But there another open, interesting question. Since I have these slides, there might be a third guy here hiding. So what we mean by that, there might be another type of resource, a resource in the thermodynamics that's not clear. When I spoke about, we don't know if Gibbs preserving covariant operations are the same as closed thermal operation. What it means is is that there might be Gibbs preserving covariant operations are very convenient mathematical quantities. They are not physical. The physical are the thermal operations, but we don't know if thermal operations has the same kind of like manipulation power as those Gibbs preserving covariant, those that are preserving the Gibbs state and also covariant. And because we don't know, there might be a third resource involved. If they are not the same, it might be that there is another type of a resource that is kind of like concealed here. But anyway, I'll have to discuss in a lot more details to explain exactly what it is, but it's a well-known, actually open problem in the field.
Yeah, I have a small question, Rupa.
Yes, Prashant, go ahead, please.
Yeah, Gilad, how does this fluctuation dissipation theorems emerge from this kind of studies?
How? I didn't hear the second one. How, what?
If fluctuation dissipation theorems,
this is actually very interesting, and it's another research area that that I know some of my colleagues actually working on. And I believe that, again, the quantum information approach to it would have a lot to say about it. I know a few colleagues that are actually working on it right now, but I haven't deeply looked into it. So I don't exactly at the moment know how to formulate it into this formalism, but I truly have a feeling that very soon we will have a very nice way of really formulating that in the terminology of quantum information. That's what I mean.
Okay. Yeah. Any other quick questions? Otherwise, it's already 9:05 here.
Yeah.
So Prashant, we close. It's been wonderful.
Yeah,
really wonderful listening to you, and learned a lot. And we'll keep talking. The others can send the questions if there are any afterthoughts. You can. The lecture will be available on YouTube, so you can go through it once more. And maybe I have to look up the archive paper, and you can send your questions on to Prashant, and maybe Prashant can forward that to Professor Gaur, if you agree to respond to some. So I think it's really nice experience for me as well. Thank you so much, and thanks Prashant for getting me to do this.
Thank you, Rupa, and thank you, Gilad. See you some other time.